All right, we're on to our third and final video on chapter 14. And in this video, we're going to wrap up talking about Diels-Alder. We're going to talk about some specific rules as to how we set up the Diels-Alder, how things must be arranged, and then we're going to move on and finish the chapter on conjugated systems and conjugated alkenes. So let's start here by looking at the rule that the diene has to be in the S-cis conformation. We saw this in the previous problem that we had done, number 20, on the end-class assignment. So we had seen that. It has to be in the S-cis conformation. If it's in the S-trans conformation, it just won't work. Now, fortunately, most of these compounds like isoprene, or which is this one right here, or butadiene, which we have looked at many times, the barrier of rotation is fairly low going from S-cis to S-trans and back. So that means we're going to get a significant number of the molecules that are in this S-cis conformation. However, we'll find that in certain compounds, rotation is going to be prevented. And that's true if we have cyclic dienes. Sometimes this can work in our favor, and sometimes it can work against us. If the alkene is locked into an S-cis position, like this one, this is called cyclopentadiene. In cyclopentadiene, it's permanently in that S-cis conformation. To show you what that looks like, I'm going to switch over again to my document camera. We're going to look at this particular molecule. This is cyclopentadiene, so you'll see the two alkenes, and here is our sp3 hybridized carbon that's at that carbon 5. And we'll find that there is no rotation about the carbon-carbon sigma bond, so this is permanently locked into an S-cis conformation. That makes it more reactive. Because it's in this S-cis conformation all the time, we're not going to it's not going to be able to be in the other arrangement. So it's always ready to go. It's always ready to go. Conversely, we can have compounds that are locked into an S-trans conformation, and that's the case with this one here. We've got this fused bicyclic system. And in that fused bicyclic system, you'll see that there is no way to rotate about this carbon-carbon bond, and so it's impossible to make these two pi bonds coplanar. And so as a result, this one doesn't do any. So this one is super reactive and goes very quickly, and this one doesn't react at all. So that just goes to show you can control how reactive it is by putting it in a ring, or you make it so it's not reactive at all by putting it in a different kind of ring. Another thing that we'll find about the Diels-Alder, the dienophile works better if there is an electron withdrawing group. Typically, that electron withdrawing group is going to be something like a carbonyl or a nitrile, but many different electron withdrawing groups will work, but those tend to work really, really well. So the electron withdrawing groups make the dienophile more or less electron dense. It removes electron density away from the diene. And so the more electron density that you move away, the more reactive it is with the electron-rich diene. So we'll find that ethylene is not very reactive. That one, we kind of have to heat it up and pound on it to get it to work. If we have a strong electron withdrawing group, something like a carbonyl, that is going to make it pretty reactive. And we can make it even more reactive by putting two electron withdrawing groups. So for example, putting two of the carbonyls on there. And we'll see that that is exactly something that we like to do. All right, so here are a couple of example dienophiles. So we need that electron withdrawing group. If we look at some of these, this one is a This one is an aldehyde, but we've got that carbonyl. The carbonyl has a permanent dipole because the carbon oxygen is very polar. Oxygen's much more electronegative than the carbon. That puts a partial positive charge on this carbon, which pulls electron density away from the carbon-carbon double bond. That just makes it more reactive. Similar thing with the methyl vinyl ketone. That ketone, the ketone pulls electron density away. And we can do this with any carbonyl compound. Methyl acrylate is another common example that is used in this fashion. We also have some that have two carbonyls, and one of these is called maleic anhydride, and this is a very popular compound to do Diels-Alder with. With two electron withdrawing groups, it makes it even more reactive, and so this particular dienophile is very, very reactive. And here with benzoquinone, we'll find that it's also a very good dienophile. Turns out that even though this is conjugated, we can break up that pi system and do a Diels-Alder with it. So this is a favorable one to do Diels-Alder with. So the key thing, and again, what you're seeing on all of these is you're seeing that carbonyl. It'll also work with nitrile, and it'll work with some other electron withdrawing groups, but the carbonyl is one of the favorites to do this with. This is a cool part of the Diels-Alder. When you do a Diels-Alder reaction, your stereochemistry is going to be retained. What we mean by that is if the dienophile has a particular stereochemistry, as is the case here with maleic acid and its stereoisomer, its diastereomer, fumaric acid. So maleic acid is this dicarboxylic acid, and fumaric acid is the same one, it's just trans instead of cis. If you have a cis dienophile, when you make that six-membered ring, the two substituents on your cis dienophile will be cis to each other in the product on the ring. So whatever the stereochemistry here is in the dienophile, you'll have the same stereochemistry on the ring. This is a consequence of it being a concerted reaction. So these end up being the same compound. This is a meso compound. You'll see we do have two stereogenic centers, but there is a plane of symmetry that goes right through the middle of that molecule. And because of that plane of symmetry, this is a meso compound. In addition to that, we've got the fumaric acid. It is the trans version of maleic acid. And when we do the Diels-Alder with it, we will get a trans product. In this case, we do form two stereogenic centers, and these two stereogenic centers have the same configuration. So they're either both R or both S. Let's see, that one is R. So this is RR, and this one is SS. But because we're starting off with achiral starting materials, we get a racemic mixture, because you know the rule, if you have achiral starting materials, we're always going to get either achiral products or racemic mixture, and in this case, we get the racemic mixture. All right, and again, the whole reason that this is the case is because it is a concerted reaction. All right. When we're doing these reactions, it's possible to form a fused ring system. So if we have a cyclic dienophile, we're going to form another ring because the Diels-Alder always forms a six-membered ring. And when we do that, we're going to get a bicyclic system. So here we start off with one ring in maleic anhydride. And with that maleic anhydride, when it reacts, we form this new ring. And so now we have a cis-fused system. All right, so it is a cis-fused system. Because the two substituents on this dienophile are cis, they're forced to be because it's a ring. That anhydride is a ring. Because they are cis, our product is going to be cis as well. So again, we refer to this as a cis-fused system. In case you're wondering, the stereochemistry here, it assists, but this is also a meso compound. We do have two stereogenic centers, but there is a plane of symmetry that goes right down the middle. So this is a meso compound. All right, this is getting kind of cool because it's possible. We talked about cyclopentadiene a little bit earlier. I even showed you the model of it. There's the cyclopentadiene. And with cyclopentadiene, when it reacts with ethylene, we're going to get a new six-membered ring in addition to the ring that we already have. When that happens, we're going to get what's called a bridged ring system. All right, so here we do have something that's bicyclic, but it's not a fused bicyclic. It is a bridged bicyclic. So this can be a little bit challenging to see, and so to help with that, I'm going to show you a couple of different molecular models to help you see what is going on. All right, so when we do this, we're going to form this ring, so we'll get a new bond between this carbon and these two carbons there. This carbon, that is the fifth carbon in cyclopentadiene, is going to be this bridgehead carbon that is right there. So it's going to be that carbon. And if we take this molecule and turn it on its side, it looks like this. All right, so let me show you this model. I'm going to switch over to this view. All right, so here we've got our cyclopentadiene, and here is ethylene. They don't come head on, which, when you draw it, it looks like it's going to be head on. What actually happens is that one is going to be below the other, and it doesn't really matter whether it's here or up here, but to make it look like the picture that we draw, I'm going to put it down here. And so these molecules will approach each other in this fashion, and when they do, we're going to break the pi bond here. We'll make a new bond between this pi bond and this, so we'll take this pi bond and go to this carbon. We'll break this pi bond and move it here. We'll break this pi bond and make a new bond going to that carbon that is in front. When we do that, what we're going to get is this. All right. So here is our molecule, and I'm going to turn it in a way so that it looks like the molecule that is on the screen. So let me go to this picture. So here you can see the picture as it's drawn on the screen. All right, right here we've got the double bond, which is represented here. We've got our bridgehead carbon, which is this top one that's up here, and then we've got these two carbons. All right, so we've got these two carbons, and there is our bridge. And then over here, we've got what was the pi bond, but is now these two carbons, and they're now sp3 hybridized. So one of the interesting things that happens in this particular reaction is that we have all these carbons that were sp2 hybridized, which included this one, this one, this one, and this one. So there, 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 and there. All four of those were sp2 hybridized. They're now going to be sp3 hybridized. And so I do this so you can see that this bond right here is in front of this bond that's in the back. The way that we draw that is that we put a little space in there to indicate that that one's behind this one that is in the front. But this is what it looks like. I encourage you to get a molecular model kit. If you've got one, I encourage you to get one. If you don't, when you come into class, I recommend that you ask to look at one of these. I'll be glad to show it to you. But get one of those kits, look at it, so that you can see that this is the same thing as this. And that's going to be very helpful as far as understanding what this structure means, what it means when you see that. All right, so there's two kinds of bicyclic systems that we can have. We can have fused bicyclic systems like this, or we can have bridged bicyclic systems. And the fused bicyclic systems occur when we have a cyclic dienophile, and the bridged bicyclic systems occur when we have a cyclodiene, so like cyclopentadiene. All right, so let's look at number 24. On our in-class assignment, switch over to our document file. Move some of these models out of the way. All right, so here we're trying to indicate what the stereochemistry is when we add this. Remember, the stereochemistry of our dienophile is going to be retained. So since this is a cis dienophile, we're going to have cis on our ring system. All right, so here we've got isoprene. I'm going to rotate that around. So there's isoprene, and then here I'll draw our dienophile. All right, so there's our dienophile, that dimethyl malate. All right, and again, I'm going to go ahead and do the arrows because I want you guys to know how to do that. So from that pi bond to carbon 1, from here to that bond to make a new pi bond, and from here to that carbon. And when we do that, our product, we're going to have a new 6-membered ring, and that new 6-membered ring looks like that. These two carbons that are across from the double bond were a part of this, and so we're going to have a cis substituents. I'm going to draw those as wedges, although you could draw them as dashes. All right, and that gives us that product. Now, technically, because of this methyl, we're going to have two stereogenic centers, and this is not going to be a meso compound. So I'm going to put plus enantiomer. So we will get the mirror image of that, and it will be a 50-50 mixture. On this one, we need to rotate that around to get the S-cis conformation. All right, so we've got the S-cis conformation. Now we want to draw our dienophile. We're going to give a little bit more room here for our dienophile. Because it's the trans. So this is our dimethyl fumarate. So it's the trans version of the malate. All right, so there is the dimethyl fumarate. And now that we've drawn that, because this is trans in our product, we're going to have the trans product. So draw our 6-membered ring. We have two methyls on there, so we'll have a methyl there, and there's our double bond. And then we'll have one of them that is a wedge, and one of them make that oxygen a little bigger there, and one of them is going to be dashed. of a dashed line. So we will get a trans product. This does have two stereogenic centers. It's not meso. This is one enantiomer, so we're going to put plus the other enantiomer. All right, on this one, we've got 1,3-butadiene. We do need to rotate it around, but we're getting used to doing that now. I'm drawing our S-cis conformation. Going to do our arrows. I didn't do the arrows on the last one. I'll go ahead and draw those arrows in real quick. So we'll start here. All right. So there are the arrows. Because we have a cyclic dienophile, we're going to have a cis-fused product. So here's the 6-membered ring that's formed by the Diels-Alder, but we're also going to have a cis-fused product. All right, so we'll get that. Sometimes you'll see these drawn as lines, and then you'll put the hydrogens in as either wedges or dashes, but this is cis-fused. I will go ahead and put that it is cis-fused. All right, we're now ready for our last rule and in discussing the Diels-Alder. And this one is one of the most challenging to see. So again, I am going to use a model to kind of help you guys see what is going on. So when we're forming the bridged bicyclic ring, the dienophile usually has a substituent, and that substituent is usually going to end up in what we refer to as the endo orientation. So we'll end up in the endo orientation. All right. To show you what the endo orientation is, well, first let me show you the screen here. So this is our Diels-Alder reaction. We've got the curved arrows here and everything. There is our cyclopentadiene, and that cyclopentadiene is going to make this bridge bicyclic system. There are two possibilities of where our substituent can end up, and those two possibilities are going to include where it is pointing down here, where the Z is closer to the new pi bond that is formed, or where the Z is pointing up, where the substituent is further away from where the new pi bond is. Well, we're going to find that when we do this reaction, we get almost exclusively the endo product. All right. So now that I've shown you what that looks like on there, let me show you what it looks like on a molecular model. All right, so here is our diene, and here is our dienophile. And as I mentioned, there are two ways that this can approach. So the molecule is going to come in either under or over. I'm showing under. But it can approach in two different ways. So here is our substituent, and this in most of the cases it was a carbonyl. I'm just putting a green atom to represent that substituent. When it comes in, it can either have so that the green atom is facing away from our system, or where that green atom, which again is our electron withdrawing, can face forward. If it faces forward, we're going to get the endo product, which is what we do get. If it's further away, we're going to get the exo product. And so this is why we refer to it as endo or exo. Exo meaning it's going away from our pi system over here. endo, meaning it's coming towards our pi system. All right. So let me show you what that product is going to look like. I will take this and put it right there, but we need to put our green substituent on here. All right, so I'm going to take this and put it there. All right, and that is our endo product. So again, over here, it approaches like this, and when it does, we make a new sigma bond between this carbon, and a new sigma bond between this carbon and this carbon, and as a consequence, that's going to flip down so that this is pointing down. All right. Just to show you how this compares to the drawing that we have, I'm going to switch back over, but we're going to do it as this view. All right, so here is our product. That's the endo product. That's our preferred product. And again, that's when the substituent comes in and is closer to our pi bond. If it were further away, then the green atom would end up here. Now, this technically has several stereogenic centers. If you take the mirror image of it, you will also get that. We're starting with an acyclic starting material, or an achiral starting material. Therefore, we're either going to get an achiral product or a racemic mixture. And in this case, it will be the racemic mixture. Oh, switch back over. I keep getting my views mixed up here. So this is the product that we get, and it is in the endo position. All right. This is the exo product, which we don't get a significant amount of it. So let's look at a couple of examples of endo addition. So the substituent from the dienophile does end up closer to the double bond and further away from the bridge. And we can explain this by looking at our transition state. So let's start by looking at what the product is. So over here, instead of this being away, it actually comes in. It's going to be underneath this cyclopentadiene, and we're going to have it where it is in this configuration. So it will be pointing down. Whatever our substituent is, it will be pointing down. And just to show you, all right, again, here it is. There is our substituent. Instead of green, it would be this carbonyl CH3 would be there. That's our preferred product. All right. If we've got a ring diene and a ring dienophile, something else interesting occurs. In addition to getting the bridge bicyclic system, because of this carbon 5 on here, because of the cyclic diene, we're also going to get a cis-fused ring. So this is a tricyclic system, and it's got both a bridgehead and a cis-fused ring. So this gets kind of complicated. But again, this is an example of endo addition. If it were exo, the hydrogens and these carbonyls would switch places. So let's look at the mechanism, and I've tried to show this to you. With the models. Here it is with drawings, and I'll put the models up next to the drawings so you can see them. And here we've got our cyclopentadiene. We're looking at it from the side, and we've got our dienophile that is coming in with an endo approach. All right. So here it is with an endo approach. So there is the Z atom, and then it's endo because it's closer to our pi system. Because this is electron withdrawing, having it close to our electron rich ring system, our electron-rich pi system here that's in the diene, makes it just a little bit more favorable, not flavorful, favorable. All right. And so it helps it so that it works a little bit better. We kind of flip this up and we end up forming this as our product. All right. If it came in from the other direction, if it came in instead of endo, if it came in exo, then we wouldn't get that interaction between this electron withdrawing group and this pi system. And as a consequence, we would end up with the exo product, and the exo product, the green would be up here instead. So we want to look at problem number 25. We'll switch over to our document camera. Get those models out of the way. And look at 25, which is right here. All right, so on this, we want to draw the product that is formed with each of these Diels-Alder reactions. All right, it is helpful to redraw this, but you don't necessarily have to, but it is helpful to redraw it so that you can do the mechanism. All right, so here we've got this methyl acrylate, which is our dienophile. We can actually draw that arrow if we'd like. So we can go from here to that carbon, here to there to make the pi bond, and then from that pi bond to this carbon. And when we do that, we're going to get, I'm going to draw this in two different ways. So I'm going to draw it in this way, because one, this way is a little bit easier to draw. All right, so that is our bridgehead carbon, and then this is the carbon that has our substituent here. So when it's endo, that's going to be pointing down, and then we'll get carbonyl O methyl. All right, that is equivalent to drawing it like this. When I draw the format that we have on the presentation, I usually draw this bond first, and then this bond, which is that one right there, and then I draw the one that is behind and draw that double bond. So the one that is behind is this carbon, or this bond right there. There's our double bond, and then here is that bond right there. All right, to indicate this substituent, we're going to go down. And then I'll go ahead and put the hydrogen right there to clarify that this one is the endo position and that is the exo position. All right, one additional thing, because this particular molecule has 3 stereogenic centers, 1, 2, 3, it is a chiral compound. However, because we started off with achiral starting materials, we're going to have a racemic mixture. So I'm going to put plus enantiomer. All right, so we're going to have the enantiomer there as well. All right, on this one, instead of having a 5-membered ring as our diene, we have a 6-membered ring, but it works essentially the same. All right, so there is our diene, and we will line this up. So this is our dimethyl malonate. right. And so there we've got there we've got our dienophile. We can do the same. We can do the same thing here. So we'll start with this pair of electrons, go to that carbon, this pair of electrons to make the pi bond, and then this pair of electrons to go to that carbon. And when we do that, we are going to get a bridged system. I'm going to go ahead and draw it again in this same fashion. Make it a little bit bigger. Making it a little bit bigger helps us to see what's going on. So we have a bridged. Sometimes we'll do it like this. All right. That's kind of ugly, but we've got two carbons there. So sometimes you'll see it written like that. So there's a carbon here and a carbon there. And then that indicates that that is there. And then we need the other things, our substituents, to get that. I'm going to draw this in this form. And the reason I want to draw that in that form is so that you can see what this looks like. All right, so instead of having one bridging carbon, we have two bridging carbons. And I have a helicopter flying over. All right, and then instead of having one substituent that's endo, we're going to have two substituents that are endo. It's hydrogen. We'll have one going down. And a hydrogen going up there. All right, it's a little bit crowded, but you can kind of get the idea. All right, to demonstrate this, I'm going to do one additional thing. I'm going to show you what the model looks like when we have those two bridging carbons. All right, so here I've got this. I've got the two carbon bridge up here. And then down here, you'll see I've got the two substituents. And so this is that structure. So I'm going to go back and forth a couple of times. So here we've got this. So the two carbons up there, you'll notice that this one is in front of that one. And here, that one is in front of that one that's in the back. And so that is that particular molecule, at least a representation of it. We've got green atoms instead of putting the carbonyls on there, but they are down there. And then these are hydrogens that are here at this point. The hydrogens are exo. These substituents are endo. This particular compound is a meso compound. You can see there's a plane of symmetry that goes right down the middle of it. If we look back at our document, it's a plane of symmetry. So it's a meso compound, which is to be expected. All right, so now we want to think about retrosynthesis with the Diels-Alder. When we're doing retrosynthesis, we want to think about what bonds are we forming, and if we sort of think in reverse, what molecules are we're going to use to make that product. The key to doing this is first, start by finding the six-membered ring that has the carbon-carbon double bond. Remember that whatever that carbon-carbon double bond is, that's going to be carbons 2 and 3 in the 1,3-diene. All right. Once you find that carbon-carbon double bond, then draw the arrows in reverse So we're going to be breaking a sigma bond, another sigma bond, and a pi bond, and we'll be forming 3 new pi bonds. So we're doing the reaction in reverse. Whatever stereochemistry is baked into our ring system, we're going to retain that stereochemistry for our dienophile. So let's look at an example. We'll look at a couple of examples here. On this first one, we've got our Diels-Alder product here. Here's our 6-membered ring. Once we locate that 6-membered ring, that means this was carbons 2 and 3 in the dienophile, and the thing that's the bond that's exactly opposite was the this is the carbons 2 and 3 in the diene, and whatever was exactly opposite is going to be in the double bond in the dienophile. And so this was part of our dienophile. So once we identify that ring, we're going to take that bond and make a new pi bond for our dienophile. Take this one to make a new pi bond there. Take that pi bond, move it over. Here we've created our 1,3 diene, and we have created our old dienophile. For this one, it takes a little bit of thinking about it to see what it looks like. But here is our bridged bicyclic system. And you'll notice here we've got these 2 substituents on there. This is where our dienophile was. This is the carbons 2 and 3 in our diene. All right, once we've identified that 6-membered ring, we do the reverse arrows, break this sigma bond, break this sigma bond, break that pi bond, make a new pi bond here, there, and there. This looks weird, but this is actually just the 1,3 diene. It's just looking at it from the side instead of from the top. I usually prefer to draw it like this because this looks really strange. And then here is our dienophile. Notice that there are 2 substituents. One is endo and one is exo. Typically, if you have a carbonyl, it's going to prefer to be endo over something like chloro. So let's look at number 53 on the in-class assignment. So we want to analyze this compound. It says give 2 different ways to prepare the following compound by the Diels-Alder reaction. Explain which method is preferred. And once we see what our 2 methods are, one will make a lot more sense than the others. All right. So first thing. All right, you'll have to excuse me there for a moment. I live near a hospital, and so there are helicopters that come overhead all the time. So I end up pausing the video a bunch of times. Excuse me for that. So we're going to take this one. This is our ring, and so we can either have this ring or this ring. We're going to start with this one. And if we go backwards, so we'll go here to there to give that pi bond. We're going to take this sigma bond to make a new pi bond on our dienophile. And then we're going to take this sigma bond to make a new pi bond on our diene. That means that would be a diene, and our dienophile would be this, quinone. All right, and so that is one of our possibilities. Now I'm going to redraw this. All right, and on this one, we're going to treat this as our Diels-Alder formed ring. And so if that's the case, then this was carbons 2 and 3 on our diene, and our dienophile would have been this. So when we do our arrows, we're going to take this sigma bond and go here. We'll take this sigma bond and create that pi, and then we'll take this pi and make another pi. And so we make 3 new pi bonds. And when we do that, we're going to get this as our dienophile, which is ethylene, and our diene is going to be this. And so you may be looking at this thinking, okay, which one is preferred? And one of them stands out as much, much easier to do than the other. And the one that stands out is going to be the top one. And the reason for that is that our dienophile has electron withdrawing groups. It has the carbonyls on them. And that's going to make it a much better dienophile than ethylene. In addition to that, this is going to be pretty difficult to make. And that's not the main reason. Our main reason is that this is a better dienophile. So I'm going to put this is preferred. And we'll say this is a better dienophile. And again, the reason it's a better dienophile is that it's got the electron withdrawing group. So that's the whole reason for that. All right, so we're going to look at something that we call the Diels-Alder diene dimer, which, I mean, say that 5 times fast. Diels-Alder diene dimer, Diels-Alder diene dimer. If we take a reactive molecule like 1,3-cyclopentadiene, we'll find that cyclopentadiene, it is such a good Diels-Alder diene that you don't need as good of a dienophile to make this work, to make it do a Diels-Alder reaction. And so you can actually have the same compound that acts as a dienophile on that diene. And when that happens, it does, it dimerizes. We get a compound that is made up of 2 of those molecules. And so those 2 molecules come together to make this. And this works so well that if you have a bottle of pure cyclopentadiene, within a couple of hours, it will be completely converted into dicyclopentadiene. And so this is what it looks like from the top. If you look at it from the side, it would look something like this. And so you get something that's kind of an unusual compound. And again, because we have achiral starting materials, we are going to have a racemic mixture. This has got 1, 2, 3, 4 stereogenic centers in it, and it's going to be, it would be a big mess of stuff. So, so even at room temperature, without even having to heat it, just at room temperature, we would get this dicyclopentadiene dimer. So that means that you can't really buy cyclopentadiene. If you want to buy cyclopentadiene, you have to buy it in this form, and you have to convert it back into cyclopentadiene. So how do you do that? Well, it turns out it's not that bad. We do what's called a retro-Diels-Alder reaction. We heat it to a fairly high temperature, and that compound will it'll break apart, and we'll get the 2 compounds, or we'll get the 2 molecules of cyclopentadiene. Because these are much smaller, they have a much lower boiling point, and so they will vaporize while this stuff is still in the distillation pot. So when you heat it up, you'll get these get into the vapor phase, and then you distill it over into a reaction vessel that has the dienophile. And as soon as this comes in contact with that dienophile, you'll be able to do the intended Diels-Alder. So again, you don't buy cyclopentadiene, you buy dicyclopentadiene. You crack it open by heating it up, and you'll get your 2 molecules of this for every molecule of that, and you will end up having this in the vapor phase. If you try to collect this and use it later, you're probably going to be in bad luck, so you want to use it right away. So you want to have your dienophile ready to go. By the way, if you ever are in a chemistry lab and attempt to do this, I'm just going to warn you, this whole reaction, it is very smelly. I've been told it smells kind of like camphor, but I don't know if I would agree with that. It definitely has a sweet odor to it, but it's very like it smells like solvent, but it's kind of sweet. When I was around it, because there was a lab mate of mine who did this reaction a whole bunch of times, and even when he did it in the hood, you could smell it all the way down the hall. I've been told, I've read, actually, in a couple different places that you can smell this compound in the vapor phase at 3 parts per billion, which I believe it. I believe it. It doesn't take much to stink up the whole lab. All right. Well, you can use this kind of reaction to do the Diels-Alder reaction and looking at retro-Diels-Alder to do synthesis planning to make things like steroid type compounds. Steroids usually have a skeleton that is 3 6-membered rings and a 5-membered ring. And we've already seen that we know how to take a 6-membered ring, or we know how to form a 6-membered ring with a 5-membered ring and a dienophile. And we know how to form fused 6-membered rings, again, using a cyclic dienophile. So it's possible to make some of these compounds using Diels-Alder. Now, as far as getting the stereochemistry, that involves some rather elegant work from some synthetic chemists. But here are a couple of targets of some hormones, hormones that have important biological consequences. Here's cholesterol, which is not one that you want a ton of, but it is an important compound. Estrone, which is a hormone. Cortisone, which is a hormone. Again, this is used as a fairly benign steroid that you can use in certain situations to help with inflammation. So making these is going to be better than trying to extract them from natural products. So you typically want to make these. So here are a couple of examples for the estrone and the cortisone. And again, it's just a partial synthesis, but it shows how you can form these backbones. So here we've got the 6-membered ring, 6-membered ring. We're going to form a new 6-membered ring when we do that Diels product adduct. You do some, it's not alchemy, but it seems like it. You do a couple of steps that will cause a ring contraction here, and you'll get a 5-membered ring, and you can get the estrone. Similar type reaction here. We use this as a dienophile. That gives you these 2 6-membered rings that are fused together, and then using a series of several steps by clever organic synthetic chemist, you can get cortisone. So we're not going to go into the full synthesis. 1, I don't know the full synthesis. I would have to look it up. And 2, there would be some complicated reactions that we haven't talked about yet. All right, we're on to the last topic in chapter 14. And this last topic is, how do conjugated dienes interact with light? In particular, we're looking at UV light, but it does have consequences when it gets into the visible part of the spectrum. So what happens when a photon interacts with a molecule? We've talked about this before when we talked about infrared radiation. With infrared, it goes from one vibrational state up to a higher vibrational state. We talked about it with NMR. With NMR, the nucleus actually flips. All right, the spin state of the nucleus flips. And with ultraviolet light, and to some extent with visible light, what happens when a photon of ultraviolet light hits a molecule is that it can cause electrons in that molecule to go from a lower electronic state to a higher electronic state. And in doing so, it raises it to what we call an excited state. Now, Ultraviolet light has shorter wavelength, higher frequency, also higher energy. This is why ultraviolet light can cause sunburn. We're actually going to talk about that too here in a little bit. When we're looking at the ultraviolet part of the spectrum, there's a range from about 200 to 400 nanometers. Now, most of that ultraviolet light is filtered out by our upper atmosphere. But if you create that ultraviolet light like in a laboratory, which is relatively easy to do, then you can do reactions. You can look at how a molecule absorbs in that section. So we're going to be looking in the 200 to 400 nanometer range. 400 up is in the visible part of the spectrum, 400 up to about 750, give or take. And then past that, we get into the infrared. So let's look at what happens when UV light interacts with a molecule. So if you have electrons that are in the ground state, the lowest energy state, it's going to look something like this, where we've got all of our electrons that are in their orbitals that they normally are. So they're in their lowest energy orbitals. And so this is sort of the normal state of a molecule. If you add a photon and that photon matches the energy difference between the ground state and an excited state, so you have enough energy to excite that electron so that it goes to a higher energy orbital, then it'll do that. If it doesn't match it, it doesn't work. Like if the photon has too much energy, it won't work. And if the photon has too little energy, it won't work. It needs to match up. All right, we'll find that the energy difference between these two states is going to depend on what kind of bond you have. For sigma bonds, the ultraviolet light is going to have to be below 200 nanometers. But for pi bonds, we can do this in the sort of near ultraviolet range, which is from 200 up to 400. So again, for sigma bonds and unconjugated pi bonds, we're going to need really, really low wavelength, which is very high energy. And that gets into a more challenging part of the spectrum. However, if we have a conjugated diene, even just a simple diene like 1,4-1,3-butadiene, the excited states, the difference in energy between the ground state and the excited state is smaller. All right. And it's small enough that you can excite this molecule to an excited state using light that is at about 217 nanometers. Interestingly, there are things you can do to the molecule that will make it absorb at a longer wavelength, and so a shorter energy difference. One of those things is to force it into the S-cis conformation. Lambda max, that is the maximum absorbance in the spectrum. And so I'm going to have to show you a spectrum to show you what lambda max is, but it's going to absorb near lambda max. So let me show you what a UV spectrum looks like. All right, on the x-axis we plot wavelength, and so this is in the ultraviolet part from 200 up to about 350 here. And you'll see that this molecule, isoprene, we talked about isoprene earlier. It's the foundational molecule to make terpenes. Isoprene has an absorbance at 220 nanometers, so 220 nanometers. But notice it's fairly broad. It's not a narrow peak, like, we get narrow peaks sometimes in the IR. We also get some narrow peaks in NMR. But here, these are fairly broad peaks. And there's a lot of reasons for that. The main reason is that the molecules are constantly moving around. This molecule is constantly going from S-cis to S-trans and back again. So it is going to absorb over a fairly broad range. So we'll find that is what the absorbance looks like. Well, that is for a diene. If you do a triene, it's going to cause this lambda max to shift further to the right and to longer wavelengths, also to lower photon energies. So the longer the conjugated system, the higher the wavelength of lambda max, and also the lower the frequency of that lambda max. So for our 1,3-butadiene, for that one, it's about 217. We saw that one a little bit earlier. If we go to hexatriene, lambda max goes up to 268. If we go another one, it goes up some more. And if we go all the way up where we have 6 conjugated pi bonds, we get all the way to 364 nanometers. This, with having a broad peak, is actually the tail of that peak. All right, like here's the tail of the peak. The tail of that peak may actually get into the visible part, and if it does, it'll cause this compound to be kind of a yellow color. All right, so the more of these that there are, the longer the wavelength. And if you get to 8 or more conjugated pi bonds, you'll actually be into the visible part of the spectrum, and that will cause your molecule to have a particular color to it. So here is an example. This one is lycopene. We talked a little bit about lycopene earlier, but lycopene has an absorbance, a lambda max at 470. So here's 470. You'll see it does absorb some here at about 500 and tails off by the time you get to 550. Well, this part of the spectrum, like 400 is violet. All right, so there's violet, and then as you get in here, this is ultraviolet down here. You'll notice it's shifted so far. It's not so much even in the ultraviolet anymore. But this is violet, and we get blue in here. We get green, and we actually get into the yellow part of the range here when we get up to about 550. That means that this molecule absorbs the violet, the blue, the green, and the yellow light. The part that it doesn't absorb is orange and red, and as a consequence, because it doesn't absorb red, it appears to be red. And that's one of the weird things that people sometimes don't realize about molecules. The reason that tomatoes are red is because they absorb all this other light and they reflect this light. Or in the case, if the light's shining through, they would transmit that light. All right, so let's look at 29, and we're almost done. We're almost done with this. Let's go to 29. All right, so which compounds in each pair absorb UV light at a longer wavelength? And so the more conjugated a system, the longer the wavelength is going to be. This one's conjugated, that one's isolated. So this one would be a longer wavelength. And I'll just put lambda instead of wavelength. All right, on this one we've got 1, 2, 3, 4 conjugated bonds. And so with this, we're going to find it's going to absorb at a much longer wavelength than this one, which just has 2 that are conjugated. So the more pi bonds you have, the longer the wavelength. This one only has 2. These are isolated pi bonds, so they will not absorb. All right, so now let's switch back over, and we're going to finish this up by talking about sunscreen. A favorite topic for me. As you've seen on the video, I have very fair skin. When I go out in the sun, if I'm not wearing sunscreen or not wearing something to protect my skin, I get sunburned really, really easily. This is because my skin is very low in melanin, and melanin is one of the compounds that's in our skin that helps to protect us from the harmful effects of UV radiation. It does not completely protect you. So people who do have more melanin than me, which is most of the people on Earth, they are going to find that they can still get sunburn and they can still have harmful effects, but they do get a little bit of protection from their naturally occurring melanin. So lucky you. Me, when I go out in the sun, I get sunburned and I suffer. And other people who have more melanin, they go out in the sun and they look they look more beautiful. Now, please be advised, I don't encourage you to go out in the sun and get suntans. Even if you don't get badly burned, you should minimize your exposure to lots of ultraviolet radiation because it can cause long-term damages like skin cancers. So just be aware of that. So here are a couple of sunscreen examples. They need to be things that have conjugated pi systems, and so here are a couple of ones that have been used. This one's called para-aminobenzoic acid. It was used quite a bit when I was a kid. This was the one that they would recommend. They would say, "Oh, it has PABA in it," so para-aminobenzoic acid. It's not quite as good at protection. Also, it tends to be a little bit more water soluble because of these OHs and NH. So it's a little bit more water soluble, so it comes off fairly easily. And that's a big reason that they've switched to things like this. This one's the Patamate, which honestly, that sounds like something that should be in Star Wars, but I don't know. So Patamate. Here, the lone pair on that nitrogen and this carbonyl are all part of that system, and this absorbs ultraviolet light, and because of all these things, it tends to be not insoluble in water and will stay on your skin for longer. So this one seems to be a favorite. Now, these are not without issue. Some of these can cause damage to things like coral in coral reefs, and so there are some places where you may not be able to use Patamate. So if you go somewhere, particularly if you go somewhere where it has a very delicate ecosystem like Hawaii or a reef off the coast of Australia or something like that, make sure you check with local rules about what is a safe sunscreen to use that won't damage the environment. All right. So sun protection factor, let's see if there's anything here I've missed. 2 sunscreen. Yeah, these are the 2 that are popular use. So one thing I want you to note, because we're going to talk about, in the next chapter, we're going to talk about aromatic systems, and these are both aromatic systems. And in the chapter after that, chapter 16, we will be looking at electron donating and electron withdrawing groups. And we'll find that these ones with nitrogen are very good electron donating groups, and the one with the carbonyls are very good electron withdrawing groups. And that helps with the absorbance of these in the ultraviolet. So it helps to block that ultraviolet light. So, all right, well, that is the end of the content for chapter 14.